Welcome to Study Loop.
So the first part of the question, A, asks us to find how long it takes for a pulse to travel the full length of a string, a pulse being simply a wavelength. So we should first find let's write this equation. Y of x and t equals, and then we have 8.5 millimeters cosine of x times 172 radians per meter, and then it'll be minus t times 4,830 radians per second. And at this point, we can simply we can relate this to the standard equation, a cosine, and then this will be kx minus omega t. And at this point, we can make some assumptions. So we have our A is going to be 8.5 millimeters. Our length is given, so we'll have 1.50 meters. And then we can say that the velocity is going to be equal to the wavelength times the frequency, of course. And we know that k is going to be equal to 2 pi over lambda. And we know that omega is going to be equal to 2 pi times the frequency. So at this point, we can say that the velocity is going to be simply the angular frequency divided by the wave number k. We can say this is going to be 4,380 radians per second divided by 172 meters to the negative first, and we have a propagation speed of 28.08 meters per second. This is simply just relating these two variables and substituting in for this. 2 pi divided by lambda times 2 pi f would simply be f over lambda, would be lambda times f, which is what we're trying to go for. Omega divided by k would give you lambda times f, which is, of course, both equal to the propagation speed. So that's how we found the propagation speed, simply from the variables of the original equation. And we say that the velocity can also be defined as the length divided by time, rather any distance divided by time. So we can say that the time is going to be equal to the length of the string divided by the propagation speed. We have the length of the string, 1.50 meters, and then we have the propagation speed, and this is going to be 0.0534 seconds. So this will be your answer. This is how long it takes for a pulse to travel the full length of the string, given that the pulse is traveling at 28.08 meters per second and the length of the string is 1.5 meters. Now, they want us to find tension. So we know that this is B. So the velocity, the propagation speed rather, is going to be equal to the force tension divided by mu, the linear density. And let's isolate F. We have V squared mu. And we know that mu is going to be the mass divided by the length. And we know that weight is going to be equal to the mass times the gravity. So at this point, we can say, okay, let's try to find the mass from the weight. So the mass would be the weight divided by gravity, and this is going to be our 0.0125 newtons divided by the gravity on Earth, 9.8 meters per second squared, and we find a mass of 0.00127 kilograms. At this point, we can say, we have all of our constants needed to approach this, and we can say that F is going to be V squared m over L, and we can say again 28.08 meters per second squared times the mass, so it'll be 0.00127, and then divided by the entire length, 2.5 meters. I apologize. Sorry, I apologize again, 1.5 meters. And this will equal 0.667 newtons. So this is going to be the tension in that string. Now, again, they're asking us to find how many number of wavelengths on the string. So we should find the wavelength. We can find the wavelength by using the wave number. So the wave number we know is 2 pi over lambda. And we can say that the wavelength is going to be 2 pi over k, or 2 pi divided by the k, 172 meters to the negative first. And this is going to give us 0.0365 meters for our wavelength. Now, all you have to do is do n, which is going to, n being defined as the number of wavelengths on the string, is going to be simply the length of the string divided by the length of one wavelength. So 1.5 meters divided by 0.0365 meters. And this is going to be 41 wavelengths on the string. So this is the max number of wavelengths that are present on the string. And then we can say, the question is asking us, what would be the equation if the waves were traveling down the string instead of up the string? And that would simply be y of x of t. We can actually do this directly. Radians per minute, and then instead of saying minus, it would be plus. So that is what differentiates. Waves traveling up the string would be minus, and then waves traveling down the string would be plus. So this would be, and then times t, 4,380 radians per second. So that would be your answer for D. And that's the end of the solution. Thank you for watching.